Roll number 15, Vinay Kumar. Roll number 17, Shagni Koja.
Present, sir.
Roll number 19, Supriya Barai. Roll number 23, Paulomi Joy.
Yes, sir.
Roll number 24, Shubham Kumar.
Yes, sir.
Roll number 25, Saurabh Das.
স্যার ওর মাইকে প্রবলেম আছে, ওর চ্যাটে লিখে দিয়েছে।
Roll number 26, Vikas Tikla. Roll number 30, Megha Sarkar.
Yes, sir.
Roll number 31, Shiv Mahato.
Present, sir.
Roll number 32, Raju Kumar. Roll number 35, Jitendra Kumar. Roll number 36, Thomas Sen.
Present, sir. 36.
Roll number 38, Chandan Kumar. Roll number 41, Jasimul Haq.
Yes, sir. Josimul Haq.
Roll number 42, Aniruddha Shah.
Present, sir.
Roll number 43, Isha Paja.
Yes, sir.
Roll number 44, Mayank Raj.
Yes, sir.
Roll number 45, Samonika Banerjee.
Yes, sir.
Roll number 46, Tanmay Ghosh.
Yes, sir.
Roll number 62, Abhishek Kumar. Roll number 55, Mukesh Kumar Chowdhury. Roll number 58, Dipanesh Das.
Yes, sir.
Roll number 63, Shubhasri Dastu.
Present, sir. Roll number 63.
Roll number 70, Deepak Bhatt.
Yes, sir. Present.
Roll number 71, Devasti Shah. Roll number 72, Madhumay Master.
Yes, sir. Present.
Anyone left giving the attendance?
Sir, roll number 15.
Roll number 15.
Yes, sir.
Vinay.
Sir, roll number 19. Sir, roll number 19.
Roll number 19. Clear word. Okay. Anyone else? Everyone get that?
Yes.
Okay, thank you.
Roll number 38, sir.
Roll number 38, Chandan Kumar.
Yes, sir.
Anyone else? Okay. So we will take up for discussion in today's class multi-stage dynamic democracy. Let's see how it works. Whether it works totally fine as per our desire, or we need to make some modifications. Or what are multi-stage dynamic democracy and how they look like? That will be a matter of time. Is the whiteboard visible?
Yes, sir. Visible.
So what do we mean by multi-stage dynamic democracy? If the output of a dynamic democracy is fed into the input of a subsequent dynamic CMOS circuit, then the whole circuitry is termed as a multi-stage dynamic CMOS circuit. So we will be having an example to explain the circuit dimension. So let us consider a two-input NOR gate first. So a dynamic two-input NOR gate. So this is a dynamic two-input NOR gate, or rather a dynamic CMOS circuit for a two-input NOR gate. So if this output is fed into by one of the input of another subsequent dynamic CMOS circuit, then the total circuit will be termed as a multi-stage circuit. So let us consider that the second stage is nothing but a two-input NAND gate. Sorry for the interruption. Let us have the second stage as a two-input NAND gate. So if that is so, then we can have our circuit like this. This is PV1, PV1, PV2, Is the circuit okay now? Yes. Am I audible?
Yes, sir.
Okay. So these are two stages, two dynamic stages cascaded with one another. So first we have stage one. So this is stage one, and the second is stage two. So you can subdivide this whole circuit as stage one and stage two. So what we find that stage two, or the second stage of this multi-stage dynamic CMOS circuit takes one input from the output of stage one, or the first stage of the overall circuit. So this is the precondition of creation of a multi-stage dynamic CMOS circuit. Then the second stage of the later on stages takes at least one input from the previous stage. So here it is a two-stage or a multi-stage, the most basic multi-stage dynamic CMOS circuit, which comprises of two stages of dynamic circuitry. So there will be a replication of both feature transistor, evaluate transistor, and output node parasitic capacitors for each of the stages. So even though I am terming it as replication, the values may not be the same. So for example, the capacity value in terms of farad for COP1 is quite different with that of COP2, because these are capacity weighted and they are beyond the control of any VLSI design. So if the designer doesn't have any control, they also do not have any control on the value of this capacitor. So the first stage output node parasitic capacitance value is quite different with that of the second stage output node parasitic. That doesn't mean that there is no chance of these two values to be same. There can be a random sequence where both COP1 and COP2 become suddenly same, but that is a rarity. Ultimately, we have a differentiation value of COP1 and COP2. Or output node parasitic capacitance values are different for both stages. Or if you have a multi-stage circuit comprising of say 100 stages, there may be 100 different values of output node parasitic capacitance for each of the stages. But one criteria is surely met, that is output of the previous stage must be one of the input of the next. So here individually we find that stage one is a two input node. So stage one is nothing but a two input node yet, but stage two is a two input NAND gate. So this NOR and NAND logic, we are using this for the sake of simplicity of our explanation. So there can be more complex logic realized within different stages of a dynamic CMOS circuit. Just for the sake of our simplicity of the further discussion, we have taken the first stage as NOR gate and the second stage as AND gate. So ultimately, Z2 represents a NAND logic of which two Boolean expressions, Z1 and B. So B is just an ordinary Boolean variable, simple Boolean variable, but Z1 is not a simple Boolean variable. That is a Boolean expression result coming from NORing of two individual Boolean variables A and B. Is it clear up to this? Is this clear up to this? Yes, students?
Yes, sir.
So one thing is certain, the portions of input potentials, either input signals or biasing potentials, which is provided by the designer, remains the same. That is the clock signal as well as the biasing potential. So the biasing potential also remains same plus VTB for both for the stages, as well as the clock signal is also fed the same clock signal. So obviously these two stages works in synchronization because you are feeding the same clock signal. So they will be having the time parameters of each of the phases, preacher phase and evaluate phase, same. So they will be having the same time period. They will be having the same timing instant when the preacher phase will start or when the evaluate phase will start. When the preacher phase will complete and the evaluate phase will complete, same timing instant they will be having because we are feeding the same clock signal to individual stages. Right? There is no difference in clock signal feeding. It is the same clock signal which is being fed to individual of these stages. As well as the same biasing potential is given to the respective node of these two stages. Is it clear? Is it clear? So let us see now how they operate. Is the whiteboard visible? I have just decreased the zooming. Is it visible, still visible, or I have to increase it?
Visible, sir.
Okay. So let us first draw the clock signal and try to analyze. So this is nothing but the clock signal denoted by phi. And so what we find, the output, if you consider the outputs individually at these output nodes as V out 1, V out 1, and V out 2. Or in other words, Z1 and Z2. But we are taking the potentials because we will be drawing the waveform. So V out 1 and V out 2 may be the output of these two individual states. So both V out 1 and V out 2 start increasing because when the clock signal is in this low phase, when the clock signal is in this pre-charge phase, when phi equals to 0, during this time there will be a charging up of output node parasitic capacitors of both these, COP1 and COP2. Both these output node parasitic capacitors will be charged up and it will be attaining a potential equal to plus VDD. So the clock signal is also having an amplitude of 0 volt to plus VDD volt. So it toggles within an amplitude of 0 volt and plus VDD volt. So I think one of you are having your microphone on. Kindly switch it off. Noise is coming. Okay, thank you. So the clock signal having these potentials 0 volt and plus VDD volt, it toggles between these two levels because these ultimately represents logic 1 and 0 volt represents logic 0. So between 1 and 0, this toggling is done of the clock signal. Now it has a certain periodicity, say capital T. Within after each T amount of time, it again rebounds. The same periodicity of the clock signal returns. So within capital T amount of time, it is segregated into T by 2 by T by 2. T by 2 in a low phase, T by 2 in a high phase. So the low phase is nothing but the pre-charge phase and the high phase is nothing but the evaluate phase that we have learned. So what happens to the output of the circuit, that is our matter of concern. So say first we are considering V out 1. V out 1. So obviously so I am just drawing these vertical lines to make sure that how the waveform ultimately shifts. Okay. So say V out 1 starts from here. Let us take a blue line for V out 1. So V out 1 initially was without any charge, so 0. Then V out 1 increases over here, reaches plus VDD, and this plus VDD remains. If in the evaluate phase, the non-logic is such that this charge will discharge, then it will go down, otherwise it will remain the same. So ultimately, V out 1 increases. So this is the charging time. This slope is nothing but it can demonstrate the charging time of the output node parasitic capacitor of the first phase. Similarly, for the second stage, that is V out 2. So for the second stage also, the same thing occurs. This slope, this slanting slope of charging time can be different. But ultimately, this also reaches to a certain level after getting fully charged up. So This certain level is nothing but plus VDD. The low level is 0 volt. Similarly, this also plus VDD. The lower level is 0 volt. Therefore, both Vout1 and Vout2 transits from 0 logic value to logic 1 value during the feature phase. What is the feature phase? Feature phase is the first half time period. So this is the feature phase. So this phase is feature phase, and this one is evaluate phase. So during the feature phase, we see charging up of COP1 and COP2. So here charging up of COP1 occurs. So Vout1 from 0 level it reaches to level 1, or 0 logic it reaches to logic 1. Similarly, Vout1 also from 0 logic value it reaches to logic 1 value. And the same situation occurs for both these capacitors. Either it will be retaining charge or it will be discharging during the evaluate phase. So what is the evaluate phase? When pi equals to 1. That is the second half cycle. So the second half cycle is the evaluate phase, this phase, this portion of the time, P by T amount of time. So individually this is also P by T and this is also P by T. So within the second half time period is termed as the evaluate phase, and during the evaluate phase we evaluate the values of Boolean values, of A, B, D, and based on that, not only A, B, D, A, B, D, and B, Z1. Here Z1 is set. So A, B, D, and Z1. Depending on these four values, either COP1 gets, depending on A and B value, either COP1 retains the charge or discharges, or COP2 retains the charge or discharges, depending on Z1 and B. Is it clear up to this? Tell me, is it clear?
Yes, sir.
Okay. So the curve during the first half time period is this. It is slanting from 0 logic value or 0 volt to plus VDD in both the cases of Vout1 and Vout2. And you can see that it slightly remains in the high logic value even within the evaluate phase, because there is always a delay in knowing that what are the inputs of both the stages during the evaluate phase. So during that time delay, it still remains in a logic high state. Only when the discharging starts, and the discharging is such that if the discharging at all occurs, mind it, then if the discharging is such that it moves, the potential Vout1 moves below 1.5 volt, then only it will transit from 0 logic value to logic 1 value. From 1 logic value to logic 0 value. Just the reverse transition towards the low logic. Now, there can be a situation that here A and B, either of A and B are 1 or both A and B are 1. So, in both the situations, or in all the cases, all the three cases, when either A is 1, B is 0, or A is 0, B is 1, or both A and B are 1. So out of these three cases, out of the total 4 cases which can happen within a truth table of a 2-input NOR gate, in the 3 cases, when any one of the NMOS transistors within the non-logic gets a gate level potential of high logic, in that stage, there will be a discharging path for COP1 to get discharged through this TE1, because during the evaluate phase, TE1 is 1. TE1 is on. And if either A or B is 1 or both A and B are 1, then these transistors accordingly will be on. So if these transistors are on, then COP1 can get a path to discharge. Now, if that is the situation, then there will be a discharging happening for COP1. Now, this rate of discharge may not be same for the rate of discharge of COP2 if Z1 and D is 1. So, in the first situation, Z1 during the p-charge phase was always on. So, Z1 was always high because COP1 during the p-charge phase was totally charged up, and V out 1 represented plus VDD. So, Z1 was high initially. Even during the start of the evaluate phase, Z1 was high. So, here there was a high logic after the p-charge phase is complete and you enter the evaluate phase. So, whether COP2 will discharge or not, that totally depended on the value of D. If D is also 1, then it will get discharged. If D is 0, then it will retain the charge. It doesn't depend on Z1 because Z1 was already high after the p-charge phase. Am I clear or not? Tell me. Z1 was already high after the p-charge phase, and at the start of the evaluate phase, these transistors which inputted Z1 was on. So depending COP2 will discharge or not, that totally depends on the value of D during the evaluate phase, not with the value of Z1. Am I clear? Tell me, is it clear?
Sir, can you please repeat it?
During the p-charge phase, both Z1 and Z2 represented a logic high value. During the p-charge phase, both Z1 and Z2 represented a logic high value. Yes, T first T by 2. This is the p-charge phase. And what happens during the p-charge phase? Both V out 1 and V out 2 became logic 1 or a logic high value, attained a logic high value. This waveform is also showing that. So it is both these potentials, V out 1 and V out 2, which is being represented by Z1 and Z2 respectively, enters the evaluate phase in a logic high value. Is it clear?
Yes, sir.
So Z1 also enters the evaluate phase in a logic high value, Z2 also enters the evaluate phase in a logic high value. So, as because Z2 is dependent on Z1 and Z1 enters the evaluate phase in a logic high value, so this transistor which inputs Z1, which gets the gate terminal potential as Z1, is on during the evaluate phase, at the start of the evaluate phase. Am I clear? This transistor is on at the start of the evaluate phase. Is it clear
Yes,
to you?
sir.
Okay. Now, this transistor with input V will be on or not, that depends totally on the value of D at the starting of the evaluate phase. Clear?
Yes, sir.
Okay. Now, if D is logic low value, then it is sure that out of the two NAND inputs, one of the input is logic low, so the output will be logic high. Am I clear? For the NAND logic, if one of the input is logic low, then the output will be logic high for the NAND logic. Is it clear or not? If one of the input is logic low for a NAND logic, then the NAND output will be logic high. That is clear or not? Yes? Please respond. Are you listening?
Yes, sir. It's clear. One input is logic.
Yes,
low,
sir.
then
Yes,
the
sir.
output will be logic.
If one of the input is logic low, then the NAND output will be logic high. Is that clear or not? Yes, please answer. Yes. Shall I ask one by one? Or you will voluntarily interact? Because if you do not interact, we cannot move ahead. One by one, please. If one of the NAND input is logic low, whatever be the other NAND input, we are not concerned. If D is logic low, the output must be logic high for an AND gate. Is it clear? Okay or not?
Yes, sir, it is clear.
Okay, fine. So here also it represents that if D is logic low and this transistor is switched off, then COP2 will not get any path to discharge. So COP2 will retain the potential it gathered. So Vout1, which was in a high potential at the start of the evaluate phase, will retain the high potential during at the end of the evaluate phase. So Z2 will represent the high logic value. Is it clear?
Yes, sir.
Okay. So the NAND gate is performing totally in synchronization with its truth table. It is performing exactly which we are desiring. Okay. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now, say the situation is such that D during the evaluate phase is not logic low, rather it is logic high. D is not logic low, rather it is logic high. Then both the NMOS transistors within the NMOS network of the second stage is in a on situation at the evaluate phase, at the starting of the evaluate phase. Why I am mentioning starting? Because at the starting of the evaluate phase, Z1 entered the evaluate phase with a logic 1 value. So Z1 entered the evaluate phase with a high logic. And that made the first transistor, first NMOS transistor of the NAND logic in a high state or in a on state at the starting of the evaluate phase. Now, if the D Boolean variable is also of a high logic value, then the second NMOS transistor in the NAND state is also on at the starting of the evaluate phase. Correct? Yes or no? Is it correct? Yes or no?
Sir, can you please repeat the last sentence?
Say at the starting of the evaluate phase, say take for consideration the second case when D is in a logic high state. First consideration was D is in a logic low state during the evaluate phase. Now we are considering D in a logic high state during the evaluate phase. Then what happens for this NAND logic? Z1 was already high at the starting of the evaluate phase. D is also high at the starting of the evaluate phase. So at the starting of the evaluate phase, both these NMOS transistor in the NAND logic is in a logic high state, or it is both the NMOS transistors are on. Yes or no? Yes or no? Yes.
Yes, sir.
Tell me if still there is any confusion. Anyone? During the starting of the evaluate phase, Z1 was already 1 because Z1 was totally charged up to represent the potential equivalent to logic 1 at the end of the feature phase. So at the starting of the evaluate phase, Z1 remains that 1 in one logic, because still there will be a certain amount of time to discharge, even if the NMOS logic during the evaluate phase is such that there is a current flowing path for COP1 to get discharged through TE1 to ground. Still, there is a delay for that discharge, and during that delay amount of time, Z1 remained on, or Z1 remained in a high logical during the evaluate phase. It is clear or not? Tell me.
Yes, sir, it is clear.
Okay. So if Z1 remained in a high logic state at the starting of the evaluate phase, and B is in a logic 1 state at the starting of the evaluate phase, not at the starting only, at the evaluate phase, then at the starting of the evaluate phase for the second stage, COP2 also got a path to discharge to ground. Yes or no?
Yes.
So what we find that COP1 started discharging during the evaluate phase as because either A or B is 1 or both A or B are 1. That is our consideration. So COP1 started discharging as well as COP2 also started discharging if D is 1. Clear?
Yes, sir, clear.
So both the output node parasitic capacitors started discharging during the evaluate phase. Now is it clear?
Yes, sir.
So again I am writing this. If D equals to 1 at evaluate phase, then COP2 starts discharging. Again, if A equals to B equals to 1, or A equals to 1, or B equals to 1. In this situation, COP1 starts discharging during evaluate phase. Is it clear? These two logic. Now, if these two situations occur, if these two situations occur simultaneously, then both COP1 and COP2 start discharging during evaluate phase of the clock. Is it clear? Is it clear, students?
Yes, sir.
Okay. Now tell me one thing. As COP1 is not equals to COP2, so their discharging rate is also not same. Yes, we can conclude that because the values of COP1 and values of COP2, these two values are not same. So their discharging rate is also not same, or their time to discharge is also not same, because that is dependent on the capacitive value. The time for discharge for any parallel plate capacitor is dependent on the capacitive value itself. So if their capacitive values are different, the time to discharge or the discharging rate is also different. Clear?
Yes, sir.
Okay. Now see a very interesting thing. Let us consider that the time taken by COP1 to discharge up to such level so that V out 1 moves from plus 5 volt to this, that is plus VDD. 5 volt is plus VDD. So plus 5 volt to less than 1.5 volt plus 1.5 volt is, so let us consider the time taken as T1. Okay, so there is a discharging time, and the discharging time for COP1 to discharge to such level so that V out 1 potential, which is the potential across COP1. What is V out 1? It is the potential across COP1. So COP1 discharges. So it discharges, it takes say T amount of time, but there will be a fraction of T1 amount of time within the total discharging time, within which V out 1 or the potential V out 1 moves below 1.5 volts. So from it takes that T1 amount of time to move from plus 5 volts to plus 1.5 volts. Therefore, from the starting of evaluate phase to the lapse of T1 time, V out 1 represents logic 1. After T1 time, V out 1 represents logic 0. Is it clear? Tell me. Because after T1 amount of time, V out 1 value moves below 1.5 volt, and that represents logic 0. But till this T1 amount of time, this is also part of a discharging time. T1 is also part of the discharging time of COP1. So this is a fraction within the discharging time. So within this first fraction, it remains from in between plus 5 volt and plus 1.5 volt. So any potential between plus 5 volt and plus 3.5 volt represents logic 1. So we can say in other words, and from plus 3.5 volt to plus 1.5 volt, it is neither logic 0 nor logic 1, this kind of a state, metastable state. So in a first simplistic consideration, we may consider that from plus 5 volt to plus 1.5 volt, it remains in logic 1. So if that remains in logic 1, then during this T1 amount of time, V out 1 represents logic 1, and after T1 amount of time, V out 1 represents logic 0. Mind it, we are considering dynamicity of CMOS circuit. We are considering the transient features within the CMOS circuit. And what is the transient features? This is the time during the transition from different logic values. We are not considering the steady state situation. We are considering the dynamic situation, the dynamicity of any VLSI circuit. So we are moving into the transient features. So when the circuit is in transition from zero logic value to logic 1 value, during that time what happens within the circuit? What is the circuit's performance? That was our main aim of moving from static CMOS circuit towards dynamic CMOS circuit. And here we are doing exactly the same. There will be a, say, capital T or maybe a capital T1 amount of time for COP1 to get discharged. So if the total discharging time, for COP1 is T1, then obviously small t1 is a fraction of capital T1. So small t1 is very much less than capital T1. And within that small t1 amount of time, Vout1 still remains in a logic high state. Only after the lapse of small t1 amount of time, Vout1 moves from logic 1 state to logic 0 state. Is it clear? Is it clear to all of you? Tell me. This discharging of COP1 takes a finite amount of time. You cannot discharge the capacitor instantaneously. So COP1 say takes capital T1 amount of time to totally discharge from plus 5 volt or plus VDD to 0 volt. Capital T1. Total discharging time for COP1 is capital T1. Then small t1 is such a fraction of capital T1 within which COP1 retains such amount of charge, at least such amount of charge, which is equivalent to a potential equivalent to at least greater than plus 1.5 volt. So it started discharging from plus 5 volt, but it will take a finite amount of time to move below plus 1.5 volt. And within that amount of time, that finite amount of time, which is small t1, Vout1 still represents logic. Got my logic or not? Have you understood what I said or not? Tell me. Anyone, if any confusion is there, you can speak out. During this small t1 amount of time, Vout1 still represents logic 1, even though COP is in a discharging phase. Did you get it? Yes, student?
Yes, sir, clear.
Did you get it?
Yes,
Yes,
sir.
sir.
Tell me. Is it clear or not? COP1 takes a finite amount of charge to discharge, finite amount of time to discharge. And that total time for discharging we have considered as capital T1. Now, there will be a small t1 amount of time within that capital T1 amount of time when COP1 discharges, doesn't totally discharge, but it discharges to a certain level where Vout1 represents not 5 volt because it starts discharging, Vout1 also value also start decreasing. So once Vout1 reaches plus 1.5 volt from 5 volt, so that amount of time when Vout1 starts reducing from 5 volt and reaches to 1.5 volt, this amount of time is considered as small t1. So small t1 will obviously be a fraction of capital T1. capital T1 is the total time for discharge, and small t1 will be obviously a fraction of capital T1, and small t1 is also less than capital T1. So during this small t1 amount of time, V out 1 still represents a logic 1 value, because logic 0 representation is something which a potential is less than or equal to plus 1.5 volt. So if the potential is plus 1.5 volt to 0 volt, this potential represents logic 0. And plus 5 volt to plus 3.5 volt, this potential represents logic 1. Now, plus 3.5 volt to plus 1.5 volt, we cannot necessarily say that this is logic 1 or logic 0. But for the sake of simplicity of our discussion, we can consider that this also still represents logic 1. So it can either represent logic 1 or logic 0, because this is metastable. This is metastable state of any digital circuit, this potential. So either logic 1 or logic 0. For the simplicity of our discussion, we are considering this is also representing logic 1. So what is the potential which represents logic 1 in this discussion? Plus 5 volt to plus 1.5 volt. This whole range of potential is representing logic 1. So V out 1 can reduce from plus 5 volt to 0 volt in a certain finite amount of time. That time is T1. Within that time, there will be a small T1 amount of time during which V out 1 reduces from plus 5 volt to plus 1.5 volt. That means during this small T1 amount of time, V out 1 still represents logic 1 value. Even though the potential is reducing due to the discharging of COP1, still V out 1 gets on representing logic 1 value. Is it clear or not? Tell me, student. Tell me, everyone, is it clear or not? The discussion up to this.
Yes, sir, clear.
Yes, Priyobrata?
Yes, sir, clear.
Priyobrata, is it clear?
Yes, sir, clear.
Yes, students, please respond.
Yes, sir, clear.
Yes, are you there in the class? Yes, Priyobrata,
Yes, sir.
Saurabh,
Yes, sir, clear.
you are there in the class?
Yes, sir.
Did you understand up to this?
Yes, sir, it is.
Yes, sir.
Yes, sir, it is clear
Or
to
I
me.
have to repeat the whole thing? Because we are in the middle of a discussion. There are lots to discuss in this particular topic. So did you understand up to this?
Yes, sir.
Yes, sir, it is clear up
Why,
to this.
why were you not responding?
Sir, we were responding. Actually, I am doing the classroom station and the mic announcements are going on. So that's why I was not keeping the mic switched
Okay,
on for
fine.
too long.
So you again go through what I have discussed in this class. Everyone, I am suggesting that you go through the total discussion of today's class, and again we'll return back and continue our discussion tomorrow. We are within a very important study of VLSI circuits, and why it is dynamic, why we are studying the transient features, that will be clear once the discussion is complete. We are in the middle of a discussion. It is yet to get completed. But I will stop my lecture of today till this. Again, we will meet tomorrow at 9 o'clock. Again, we will meet tomorrow at 9 o'clock in the morning and complete our discussion on this topic. Okay? Is it clear?
Yes, sir.
Okay, thank you. So let me stop my class up to this. You go through what has been told in today's class, revise this up and come again tomorrow morning. We'll continue our discussion and we'll be concluding in a very interesting feature of VLSI. Okay? Is it clear?
Sir, I have a question. Will the propagation delay be also covered?
We
Because
are
we are considering
we are considering a delay which is more minute than a propagation delay, because we are dealing with the discharge of a capacitor within a transistor level circuit. So no question of a gate propagation delay. We are within the middle, within the inner circuits of a logic gate. And here the discharging delay is being considered. The discharging delay of a capacitor. Okay, this is not a propagation
Okay,
delay.
okay,
This is just a discharging
okay,
delay of the capacitor. Okay.
okay, sir.
So we have just learned what is the discharging delay or how the discharging takes place of the first stage. In tomorrow's class, we will continue with the discharging pattern of the second stage, and then we will be comparing both the stages and conclude with a very interesting fact. Right?
Okay, sir.
Okay, thank you for listening.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.